Okay. So I'm going to talk about MOM6 interfaces for DA, and this is really a status report. Things are continuing to evolve. I just want to talk about what we've done to date and then where we hope to go in the future. This is based on work with large contributions from Fei-Yu Liu and Tony Rosati at GFDL, and then folks at AOML, where we've been looking at Parada data specifically. So I'm going to talk about that Parada. Okay. So, oops, okay. So the outline for the talk, I'm going to cover two paradigms for data assimilation, running in core and out of core. And then I'll move into talk about our GFDL Spear coupled data assimilation system that's using MOM6. And then a motivating example for, I think, why we really need to improve our observational diagnostic capability, at least as far as what we're doing. That seems to be an area where we could all work together on. So after discussing that motivational example, I'll talk about MOM6 DA interfaces as they currently exist, and then community DA software and how we can interface with that, and then summary and future plans. So the two paradigms for data assimilation are in core and out of core, or online and offline. Online DA, you run an ensemble or a single realization that are executed concurrently, and then the DA is performed via communication calls through memory. The offline mode, you're running, again, either an ensemble or a single realization, and then storing the results periodically to file, and then you perform the data assimilation by accessing those files, calculate your model increments, store them to a file, and then read them back into the model, or modify the restart files. So the choice of whether you're doing things online or offline depends on your resources and goals. So if you're interested in getting the highest resolution you can afford on your platform, then you might opt for an offline solution where maybe throughput is less of a concern. If you're concerned about throughput, and you can store your full ensemble concurrently in memory, then that's a choice that you can take. So the type of filter methods that Daniel just discussed, I kind of categorize them as sort of ensemble-based filters and tangent linear models, and then determinists, and that's where you're using the model uncertainty to derive the prior covariances, or a deterministic filter, statistical interpolation, where you have some prior covariance model that you're using that's not a function of the model state. And then adjoint models, which I'm not going to cover. Is that fuzzy? Okay. So the GFDL Spear system, it's been recently developed. It's described in a paper by Delworth et al. In James 2020. And then the paper that's under revision by Fei-Yu Liu et al. And also to James. And so this is running operationally at GFDL. We're using online ensemble-based data assimilation within the coupled model. We have 30 ensemble members. The ocean resolution is nominally 1 degree with enhanced Arctic resolution and 75 vertical levels. This model is atmospheric heavy, so the atmospheric cost is a lot higher And this is running with a C96 atmosphere with 33 levels. And so 36 ocean processors are used per ensemble member. We're using a total of over 4,000 cores. And then a subset of those cores are used for the actual data assimilation part of things. And we're running this for several months to a year at a time. So the SPEAR system we're using in-house developed QC. I mean, we are reliant on QC flags from, for instance, for ARGO from the data access centers, and QC flags from the mooring folks. But we have additional QC that we're using. We have our own software for streaming the data from remote sites. The actual filter code is developed in-house. The system was developed more than 15 years ago for MOM4 and MOM5. And then we transitioned in the last couple of years to MOM6 and made some updates to the code. So for the SPEAR example, we're only using ocean data to constrain the model. So the atmosphere is unconstrained. And then this kind of helps to address the issues that we heard about previously with filter collapsing. The filter is collapsing. The model's becoming too uncertain because you don't have enough uncertainty in the forcing. So we're experimenting with this approach of trying to just use the ocean data, and it works pretty well. But there's some issues, and I'm going to go back here to this previous slide, and I've highlighted in the Atlantic. I'm sorry. So in the top here, we're looking at pentadal differences in 0 to 2,000 meter heat content in for the recent 5-year period from 2013 to 2017, minus the early 2000 post-ARGO period from 2005 to 2009. So we can see that there are a couple of things that were suspicious to us. Oops. So we have this this cold, this cold anomaly in the eastern tropical Atlantic. So we wanted to look at that a little further. It seemed a little suspicious to us. So we've been doing some post-analysis to try to figure out what's going on. So SPEAR, so basically, Frank's question at the end of the last talk about what data is, what are the gaps in the data? I mean, by far, ARGO is the most important data source that we have, and we can see that I think the models generally are much less uncertain post-ARGO. Prior to ARGO, there was a lot less data. The observing system was much more heterogeneous and hence larger uncertainty. So I think going forward, the thing we can do is continue to invest in ARGO. So in addition to assimilating ARGO, we're also assimilating mooring data. And this is a diagram of the current status of the mooring array. And occasionally, mooring stop transmitting data. There's either some damage to the mooring, mooring gets lost, what have you. So there are these gaps that exist. So one of the things that concerns us is, as these moorings are coming on and offline, what's that doing to our analysis? So this is just looking at a time series from the early 90s up to present in the Gulf of Guinea at the equator along the Greenwich line. And at 60 meters, and so the black lines are the model individual ensemble members. So these are all 30 ensemble members. And the red lines are the sphere, or the Parada data. So you can see that the Parada data comes on sometime after 2000. And there are periods where we have gaps. The ARGO data comes online sometime around 2004. And so prior to those periods, we were mostly relying on XBTs and occasional CTDs. So I'm going to focus in on this period. So I was showing this pentatile difference in heat content. So we're interested in looking at this early 2000 period where things are relatively warm versus the latter few years where things are cold relative. So looking at this early period where we have a gap in mooring data, we can see that the moorings, the mooring drops offline sometime in early 2004, and then you can see that there is a large, this sort of ensemble spread increases after the mooring drops off, as you'd expect. Then it comes back on sometime mid-2005, and then we see a collapse of the ensemble spread. But overall, it appears that, at least at this depth, in this location, the model is biased somewhat high relative to the mooring data. And if we look at the latter period, after, between 2012 or so and 2015, then here we're seeing periods where the model and the mooring are agreeing fairly well outside of this 2013 to 2015 period where we have a cold bias. So, we have, at least at this location, we have a warm bias early on in the 2000s and then a cold bias later relative to the moorings. And I think that's accounting for, that's consistent with this pentatile drift that we're seeing, or the pentatile difference. So, we wanted to assess, so there's a potential that moorings coming on and offline could be contributing to the model mismatch. Also, changes in the ARGO observing system could be the cause. So this is a plot showing ARGO samples with depth. So this is upside down, I'm sorry, but the surface is at the bottom and 50 meters at the top in each panel. And then time is on the horizontal axis. So this is just showing locations where we have ARGO samples within the equatorial region from 10 south to 10 north in the Atlantic. And you can see in 2004, the coverage is fairly sparse, and then it increases over time. And the sampling is fairly good in the latter period and fairly consistent. But still, nonetheless, that's a potential issue for us. So what I'm illustrating here is the need, I think, for more detailed observational space analysis and to sort of do a post-mortem of what happens after we run these DA applications. So we want to improve our observational space diagnostic capability. This would include things like outlier detection, looking for spurious ensemble inflation, and then multivariate analysis, looking at multiple fields. We're also working to improve our observational QC. I mean, this is an ongoing issue for us in trying to improve our QC, and we have uncovered problems with the observational data at times, and we've tried to feed that back to the data centers, but it's a lot of work to deal with observational systems. They're messy. So the question is, can we better achieve these goals using community-based DA tools? So those would include DART, as we just heard about, and there's the JEDI project from JCSDA that Travis is going to discuss next, and there's the parallel data assimilation framework developed at the Alfred Wegener Institute in Germany, and there are others, I'm sure. So there are already community projects for data assimilation, and how can we link to those? And then separately, there's infrastructure that's going to be required for data assimilation that's more specific to MOM6. Can that infrastructure be developed in a way that we can support the various community software applications? So in a nutshell, what we need the DA infrastructure to do from a MOM6 point of view is to gather the ensemble states, if you're using ensembles, so that's either done online or offline through restarts, and then the vertical remapping. So as we all know, MOM has a generalized vertical coordinate system. The vertical grid is evolving over time. Individual ensemble members are going to have different vertical grids. So it's convenient and probably, I'm not sure it's necessary, but certainly convenient to have a common analysis grid. So that's part of what we're trying to accomplish with the DA infrastructure. So the interfaces that we currently have are a call to initialize the data assimilation. These are this would be called from MOM6 if you're doing it online. And for that, what that would do is it sets up a vertical grid for data assimilation, and it does the horizontal domain decomposition across processors for the analysis. And it allocates a data assimilation control structure, which is not really, it's not seen by MOM6. It's sort of not at the top level of the model. It's buried a little deeper. And then that loads local observations. We also support a wider halo for the analysis. So the actual model halo is typically 4 points. If you're trying to incorporate observations that are spatially not adjacent to the model grid, the current model grid point, then you need to have this wider halo just to accommodate your covariance length scales that you're using. There's a set prior tracer call that's it's made from the model, and that would copy the ensemble members, individual ensemble members into an ensemble state vector. There's a call to get the posterior tracer, where you would typically return the increments. There's also a call for retrieving a tendency adjustment, and that would be relevant, for instance, for offline applications where you want to save your increments to a file and have them come into the model, say if you're not trying to modify the restarts. So there's this thing that's often used where instead of supplying the increment all at one time, you might choose to distribute that over the analysis step. So you could do that through this call to get the tendency adjustment. And that would retrieve the adjustments from the analysis vertical grid and then perform the remapping to the current vertical grid. There's a call to the main ODA routine, which is called at every analysis step. This is where you would gather the profiles that you currently need, run the filter code, retrieve the increments, and then apply them to the model. These are the way the calls look. So these are the calls that are actually made from the MOM.F90 level. That's the top level for MOM. So the init ODA, the set prior tracer, the ODA call, which is done in every analysis time step, and then apply ocean tracer increments. And then this last one is for setting the analysis update. Okay, so a couple things to note here for init ODA. The way the vertical grid is defined for MOM, you write a parameter file, and then that parameter file would contain instructions on what grid you want to use. So the forward model might be using a hybrid vertical coordinate, but you'd want to use a different coordinate for your analysis. So that would be done typically with the Z coordinate, and you can do that in MOM because you can. It's flexible enough that you can read from different parameter files. So you can actually assign an ensemble ID to each process, and so each ensemble member could get a different set of parameters, and ID 0 would be for the filter. So that's where we specify the parameters for the data assimilation. So it's pretty convenient. So the lower level framework has a control structure that's private, so it's not seen by the higher level modules. And basically it just has a bunch of types for storing the prior state, and the posterior corrections, the profile data, and a bunch of other information. So it's a big data type, but that's kind of what we're using to communicate to the lower level code, which is an external repository. So the previous routines here, these top level APIs, they have to be seen by the model, and the lower level APIs are going to exist kind of separately in external repositories. So what we're currently using, we have 6 routines. There's nearest neighbor search that's actually taken from the JCSDA repository, and that's a KD tree search algorithm that Travis Sluka provided us. Thank you, Travis. And some functions for localization and distance. A core module that's actually gathering the profiles. We have a type definition for the different observation types, and a write ocean observation module if we want to write our misfits to disk, and then the actual ensemble filter code. So I mean that's our software stack, but I mean we want to think about how we can interface with these community-based DA tools. So JEDI is there's a lot of effort going on there, and I'm trying to learn how to use it. And the way they work is through containers. So you have basically everything, all the models, the individual models, all the code is compiled into libraries and stored in a container. Everything at its basic level is in a Docker container, and then those are used by either Singularity or Charlie Cloud, which are sort of like VMs, I guess. And then there's also Travis integration. So it's this is not the way we currently work at GFDL. So kind of it's potentially disruptive to kind of work within this framework, but we are trying to assess how we can do that and if it's feasible. And what we really want from this are things like a common software for marine data access and quality control. I mean, there are multiple data types that we could use that would include altimetry, sea surface temperature from satellite, ocean drifters, surface drogue drifters, ARGO drifters, moored data, sail drones, and the list goes on. So we want access to all that marine data, but it's difficult, as I mentioned, to maintain the tools to do that. So we're really interested in leveraging that capability. So where that exists within JEDI is for data access. It's this IODA layer, and what that's doing is feeding data from EMC, NCEP, NASA, Met Office, and processing that and writing it out into a form that's ingestible by JEDI, and then that output works with the lower level functions. The UFO is a unified forward operator, and the OOPS layer performs other DA functionality. So that's a layer that I think would be useful for us to access. There's also Dart, which is all Fortran based. It's self-contained, well documented, implemented in SIS2 by folks at GFDL, and MOM6 applications, I'm told, are coming in CESM. So I'd be interested to hear how that goes. So in summary, the interfaces that we have to support both online DA and offline DA, which need to interact with the model. It can't solely be done through restarts. And we think this can be done through a simple set of APIs, similar to what we currently have. And we're looking to support this for other applications. I wouldn't say that it's ready at this point to do that, but we want to make sure that we can support those things within MOM6. And we need, in general, just support for community DA software. We need to get away from in-house development, particularly for data streaming and QC. And we're going to continue to further evaluate JEDI for integration into how we use DA at GFDL. So that's all I have. Take questions.
Thanks, Matt. Luann Thompson had a question. then had to leave, so I'll read the question. Is there a way to assimilate altimetric sea surface height into the system, which I think she means, I think, your SPEAR era or generation system. You mentioned this later in the talk. This would increase high quality data coverage back to 1993.
Yeah, I mean, the challenge with altimetry assimilation is projecting that information into the subsurface. So getting reliable covariance models for sea surface height and the tracer variables. So I don't know that that's really been tried in earnest. My feeling is that you would need some sort of ensemble system to do that. But yeah, so it's possible in principle, but we haven't done that yet.